Alright, so today I just want to prove the Mcallister Theorem, which is very important for PAC Bayesian learning. So we start with PAC learning. There is no Bayesian thing because we should focus on the necessity of this. So we have a probability distribution. And what is the probability that your hypothesis, this is hypothesis, for example, your favorite classifier, and this is the true ground truth. So it's we call it a concept. What is the probability that your concept says a difference? It says a different thing than your hypothesis. For example, here it says she has a cancer, but this one says, the blue one says no. So we have lots of false positive, false negative, and those things. And so with high probability, but among all of these things, with high probability, we can achieve a low generalization error. So greater than 95%, or the error is just less than, for example, some threshold, the probability that is less than epsilon is greater than 95%. So we want to avoid false positive. So when I say error throughout this lecture, I mean the probability that the truth is different from your hypothesis. And if I just prove the Hausler theorem, we can understand where we are going. So for target concept C, if H is finite, which is in some cases, and D contains M-independent random samples, the probability that exists hypothesis H such that the error is zero, I mean training error, assume that your favorite classifier, you have overfit everything and your training error is zero. But your true error is greater than epsilon, which is bad. You have crossed the threshold, the red line. So that probability should be very small. And this is less than the cardinality of your hypothesis space and an exponential of epsilon and m. For example, you have m data points and you know the threshold epsilon. So the proof is like this. We want to prove this, proving this. Prove it. So how likely is a bad hypothesis to label m training data points right? So it should have the probability of error should be greater than epsilon and labels one data point correctly. So for one data point is less than 1 minus epsilon. So it's like an inductive proof. But because they are independent, so for one data point it has 1 minus epsilon, the other data point 1 minus epsilon. And how many data points do you have? We have m data points. That's why it becomes this. So it is upper bounded by 1 minus epsilon to the m. And so there are many possible hypotheses. That's not the only one. So you should consider many different hypotheses because someone else could pick another hypothesis. We want to take into consideration of all of them. And how likely is the learner pick a bad hypothesis? So we use the union bound because the first hypothesis should cross the red line, the second one, or any other one. But if you use the union bound in probability, some events A and B, so we can sum that, and that's why this is upper bounded by this term. And as I said in the previous slide, each one has 1 minus epsilon probability, and because we have m of them, so it is 1 minus epsilon to the m, but it is just for one of those hypotheses. We have k hypotheses, so summation over k. So k of them. So this is the reason for this. And finally, we tend to approximate this k by the cardinality of your hypothesis. I mean, the complexity of your hypothesis space could not be that much because k is at most the cardinality of your hypothesis space. So we change the problem to another problem. We don't know k, but we say, okay, let's call it h, cardinality of h, okay, here. And finally, you know a simple fact from elementary calculus, so this becomes h. So the proof was very easy. So let's come back to PAC learning. We assume that training is 0, and so all of these is for, so the error is upper bounded by epsilon. And from that theorem, Hausler theorem, I said that this one is upper bounded by cardinality of h times that exponential term. And you can write this as m to the m greater than something, and finally you can write the error true to be bounded by this term. So this is the starting point of articles of Mcallister. So we assume we know such thing. And in learning theory, you know, we have Bayesian inference and we have PAC learning. If we combine these two worlds, because this one is generally for frequencies. Bayesian inference is for Bayesian. So if we combine it, we call it PAC Bayes, frequencies Bayesian. And so it's always a black box. You don't know the model. So using input, you give input output and you get the concept model. So Bayesian algorithms are highly effective when the Bayesian assumptions hold out, can overfit when those assumptions fail. So the first preliminary theorem of Mcallister in his nice article, this is the error bound of 1. So the same when U is singleton. So if U is singleton, it reduces to this. So C, instead of U is singleton. I mean, it only contains one hypothesis. So it reduces to this one. So this is the theorem. This is the theorem. And so we want to minimize this bound. So with at least 1 minus delta probability, this holds. We can think about it as, of course, this is PAC Bayesian model averaging. This is the title of one of the articles of Mcallister. And we select a weighted mixture of the concepts. It's like aggregation, as you are familiar in machine learning. There are aggregators. You have a bunch of classifiers. You don't know which one is better, so you aggregate. So it is the same thing, but here is the mathematics of that and how it helps for a better generalization. A weighting that minimizes the provable loss bound is formally analogous to classical Bayesian posterior distribution. So when we say loss of C and S, it means the sum over all of these points inside S. If Q is probability distribution, when I say L of Q, it means Qi L of C, because each of these Q1 times the loss of first classifier plus Q2, the probability that this one is chosen, and the loss of the next hypothesis is this, and we add all of them because it's a mixture of classifiers, for example, or mixture of some hypotheses. So it is logical to think of laws as an aggregation of all of the things. So it's a trade-off between sample complexity and concept complexity. Very beautifully is shown in this slide. So this is concept complexity. What is the complexity of your, for example, neural network? How many neurons are you using? Billions of neurons? So this concept complexity could be very complicated. PI here, the probability of choosing that I's concept. And sample complexity, so let's apply that concept, that hypothesis, to the samples and see what. So it is really about data. So both of them are about data dependent, but you can think of this as, for example, if you put prior on something, we don't care about the data. We have not even seen the training data, but we put prior on that. And this is a model selection. And the definition of pruned distribution, which is used in this theorem, is that for just ease of use, we use this. And I recall that the divergence is this, and so here we want to minimize this term. So L of Q is just the weighted of them, and L hat for L hat is the weighted of L hat, and so I recall these things. So now you're ready. Here is a slide that I provided to show that all things could be, of course it is very hard to show, but it is somehow equivalent to what we do in classical Bayesian posterior distribution. So Z, which is hidden and we don't know, is weights of neural net, and Q of Z is a distribution over these weights in order to construct the hypothesis space. So you see that the bound is not far away from So the theory of Bayesian posterior distribution, variational inference in general, is very closely related to PAC Bayesian learning. So we always want to know which posterior satisfies this optimization, because after all, it's an optimization problem. Which posterior? Q is the posterior, P is the prior. Which one minimizes this? So it is the log. So as the log evidence is fixed with respect to the posterior, so maximizing L of Q minimizes the KL divergence. And another article of Mcallister is PAC Bayesian model averaging. And it repeats all of those things, but here it is upper bounded by this term. And we know the optimum solution. We know it's a Gibbs distribution. So it is just a statistical mechanics which is used for machine learning. So you might say, okay, you know the distribution, you know the answer, you know the best posterior that you can imagine, so why are we talking about it? But this one is intractable, as usual. So everything that is good in machine learning is intractable, and we should approximate it. So no free lunch. So the proof sketch of theorem 1, first we used lemma 2. So I'm trying to prove the Mcallister algorithm as I promised in just 4 slides. 1, 2, 3, 4, 5, 6, 7, 8. 8 slides, but roughly it's just 2 slides. So we start by lemma 2. Lemma 2 here, we start by this one. And then, so we want to minimize this bound. What should we do? First of all, we just prove that this delta, which appears here, this delta, it has exponential of that has a bound. So we have bounded that. At least we have bounded that. And then we look at that and say that we have lemma 3 that says if this holds, then your posterior times all of these delta I, because we have n different concepts, n different hypotheses. All of them are bounded by this. And using lemma 4, we can show that we relate those QIs to D, Q, and P. The KL divergence between Q and P. And we maximize it. We maximize it to have a better generalization. And in maximization, we always use Kontaker. And those KKT conditions that I have explained in optimization playlist. And it is constraint optimization because of this constraint. And if you combine all of these things, you will see that Mcallister algorithm is just this simple relation. So this is the proof of lemma 2. And we use Chernoff bound for a random variable. It's like applying Markov